Hi, I'm Dr. Don Stolman, and today I want to talk about two of the most famous, I guess, decision models in finance in terms of capital budgeting: net present value and internal rate of return. Okay, I'll be going through some of the calculations and showing you what this is all about. But a couple of things, housekeeping things that I want to talk about first. If it's been some time since you've had experience with time value of money, present value, and so forth, or if you want to refresh your memory on this stuff before I get into this, you might want to stop the video and go into course documents, because I did 3 videos in course documents on time value of money. So that's a very good review for you if it's been a little time since you've experienced time value of money, especially the 3rd video, which solves for things on the right-hand side of the equation and so forth, and it's present value stuff anyway. So you might want to do that before you go ahead and watch the video. The other thing I want to remind you about is, back out of here, there are pages in the back of your book, in the custom book. It starts on page OM23, and these are the pages on capital budgeting that I wrote. Right before that was the pages on cost of capital. This is the pages on capital budgeting. So those are things that I want you to make sure that you're aware of, and you might want to read that first before going through the video. Okay, let's talk about net present value. Actually, there's 3 types of capital budgeting problems. One is simple payback, and I'm not going to go through that in the video. It is simple, okay? Hopefully you've already read through that. That's fine. Net present value, internal rate of return take a little bit more explanation, and that's why I want to do this video on these 2 topics. Net present value. Net means subtract. What we're going to do is we're talking about investing in big ticket, very expensive, maybe multi-million-dollar projects. The type of project you do not want to make a mistake with. Now, the formula that I'm going to use is very simple. It's what I use in the back of the book. It's not what they use in Chapter 10 of your textbook. They have a formula that's very, very involved. I'm going to make sure that all the cash inflows are the same amount of money. Now, if you remember something from time value of money, if the time is the same when we're going to receive something and the dollars don't change, you have what is known as an annuity. So I'm going to be using an annuity. It makes the number crunching very simple, but it still gets the point across beautifully, I think. I've been doing this for a long time. So here's the formula for net present value. NPV is going to be equal to the cash flows we're going to be receiving from the project. This is the profit from the project. We've already subtracted out the costs. Okay? So every year we're going to get this amount of money, the cash flow, times the present value interest factor of an annuity, because we're going to be receiving this money over time, and as you know, it shrinks over time. The subscripts I'm going to be using will be R and N. Now, you're familiar with N because that's the number of years something's going to run. R is a little different, though. R is the cost of capital. All that stuff from Chapter 9, the weighted average cost of capital, here's where it plugs into this equation. From that, we're going to subtract, here comes the net, the cash flow. I'll put a 0 here today. This is the cost of the machine or the factory, whatever it is. People are paying for it today. So really what this is saying is, if we use this in a timeline, and let's say n equals 8. I'm using 8 years. Okay. 1, 2, 3, 4, 5, 6, 7, 8. And let's say the cash flows coming in are $50,000 a year. So every year we're getting $50,000. Those are all 5s. What we want to do is figure out what are the values today, presently, of those $50,000 cash flows. Yes, we're going to get $50,000 for 8 years. That is $400,000. But on a present value basis, it's not that much money. It's being discounted by the cost of capital. So what we want to do is figure out what the values of these cash flows are, this part of the equation, and then we're going to subtract from it the cost of the machine. And quite simply, if the value on a present value basis of the incoming cash flows exceed the value of the machine, we'll do the project. And if the cash flows are less, that means we'll lose money. We don't do the project. It is a decision model. Accept, reject. So the numbers, $50,000 coming in. Let's say the machine costs $250,000, $250,000. It lasts for 8 years. And let's say when we did our cost of capital, the board of directors said, let's just sell new stock. Now, you know from cost of capital, that can be very expensive. So they just decided to just sell new common stock. Don't take on any debt. Okay, let's see what happens there. The cost of capital for selling new stock, let's say, is 13%. So 13% goes right here. We go into the present value annuity financial table, which is S4, the last table of your financial tables. And if I did that correctly, I'm going to find that that factor comes out to be 4.799. Okay. So I'm going to multiply 50,000 times 4.799. And if memory serves, I did that ahead of time. You're back. 50,000 times 4.799 is 239,950. So the value of this project to the company is 239,000 and change, but we're going to pay 250 for it. Minus, well, it doesn't take a genius to figure out we're losing money on this project. We're going to lose a minus $10,050. So in this case, net present value is equal to a negative 1050. Here's the decision model with net present value. If net present value is positive, all things being equal, we accept the project. If it is negative, we reject the project. In this particular situation, we would not do this project because we'd lose money on it. So all is lost. We can't do anything else. But wait a minute. I said we did this project by selling new common stock, and that's the most expensive type of capital that you'll learn from Chapter 9. Well, wait if they go back to the drawing boards and said, hey, wait a minute, just kidding. Let's blend in some debt, which is the cheapest form of capital. And when they did that, they blended some debt and some common equity. Let's say that changed the weighted average cost of capital and brought it down to 10%. And we redo the calculations. The only thing that's changing is that 10%. Now when I go into the chart, 10% rather, 8 years, my factor comes out to be 5.335. 5.335 times $250,000, times $50,000, the cash flows, comes out to be 266,750. 266,750 minus $250,000 is a positive 16,750. All of a sudden, I have a positive net present value, and now I can accept the machine. I can accept the project. By the way, that was why cost of capital was so very important and how they blend it and target capital structure and all that. But this is a very simple calculation of net present value. Okay. So this is the first decision model I'm going to talk about today. The other is called internal rate of return, and as we'll see, it's just a variation on this formula, but it gives us a slightly different answer. You see, net present value gives you the answer in dollars and cents. All right? And that's fine, and sometimes that's good, but oftentimes management wants the answer in percentages, as in a rate of return. Right? So using this formula and modifying it just a little bit, this gets a little tricky. Okay? We're going to end up with a rate of return, a percentage, instead of a dollar amount. Now, we do that by switching to something called the internal rate of return, which uses this formula, but what it does is it sets net present value equal to 0. You're going to have to think about this for a while after the video, why this works. The number crunching is fairly straightforward. Why it works, it's going to take a little thought on your part. But we set net present value equal to 0. So the internal rate of return is equal to this formula. But now net present value is not the unknown term. It's 0. The unknown term is going to be right here, that little r term. In the net present value formula, we call that the cost of capital. Here we call it the internal rate of return, and it can be different. Now, bear with me, I'll explain why that is so. Let's plug the numbers in. I'm leaving the rest of the numbers alone. Okay. So we have 0 on the left-hand side of the equation. We're still getting $50,000 in each and every year. The machine is still costing us $250,000, and N is still 8 periods of time, or 8 years. I don't know what the internal rate of return is. So what I'm going to do is I'm going to take this formula and I'm going to solve for the subscript R. And you saw that in your previous finance course. Or if you watched my videos, you saw that in the third video. I solved for a rate of return, or I solved for the number of years. It's fairly simple to do. Just remember a little bit of algebra. Okay? This is my unknown term. I need to isolate that unknown term. So the first thing I want to do is get rid of that 250 by adding it to both sides of the equation. By adding it to both sides of the equation, I get 250 over here, minus 250 plus 250. That comes off entirely. And now here's my equation. 250,000 equals 50 times this thing in parentheses. Well, the thing in parentheses is what I have to isolate. So I got to get rid of the 50. Divide both sides by 50. $250 divided by 50, I made the numbers nice and easy, okay, is 5, correct? Or 5.00 if you like a couple decimal places. That is the present value interest factor of an annuity, R, internal rate of return, for 8 periods of time. Now if you go into chart S4 and read across 8% and start reading down, go 8 years and start reading across, okay, getting ahead of myself, you will bump into a number very, very close to 5.00. It's 4.986 or something like that. And that 4.9 number, if you read straight up to the percentages at the top, remember that, is very close to, I believe, 12%. What that is saying is, if I invest in this project, I am going to make 12% rate of return. So, how do we use this as a decision model? Well, with internal rate of return, we're comparing what we just calculated to what the cost of capital was. Now, I used two cost of capitals earlier. I used a 13%, and I used a 10%. Well, if my cost of capital was 13%, that was using all common stock or something, and my internal rate of return is 12%, then my internal rate of return is less than my cost of capital. If that is true, I reject the project. That's the decision model for internal rate of return. If the internal rate of return is less than the cost of capital, I'm going to lose money. Reject it. If the internal rate of return is greater than the cost of capital, I will accept the project. So that first project that I did with net present value, that I rejected because of net present value, because it gave me a negative number, a negative dollar amount, I'm also going to reject with internal rate of return. And guess what? Most of the time when you run both models, net present value and internal rate of return, they will give you the same decision. There's one small case that I'm not going to deal with in this course. If you really want to know about it, your textbook talks about it. You have to do net present value profiles. Trust me, you don't want to go there right now. But internal rate of return and net present value for our purposes will give you the same decision. So in this case, we would reject it. But with a 12% internal rate of return, when we switched over to using debt and blended the debt into our capital structure, our weighted average cost of capital, so that we dropped the cost of capital down to 10%, then internal rate of return was greater than the cost of capital, and we accept the project. Just like we did with net present value, because net present value came out to be a positive $16,000 and change. So those are your two basic models for capital budgeting. Very famous, used all the time. A couple of last points I want to bring out here. When you read through the chapter, you're going to see two terms, independent and mutually exclusive, as in projects. Let's say we have 3 projects. I'll give you the net present values. I could give you internal rate of returns either way. I'll give you internal rate of returns. 13%, 12%, 8%. Right? Here's my internal rate of returns. My cost of capital 10%. Now, from what I just discussed, my cost of capital is 10%. A and B are okay. They're both greater than, so I could accept both projects. C I'm going to reject because it's less than the cost of capital. But here's where independent and mutually exclusive come in. If projects are independent, they are evaluated independently from all the other projects. In other words, if you've got more than one that meets your criteria, you can do more than one. So if I'm talking about independent projects here, A and B are independent, we're going to do both projects because both of those meet the internal rate of return criteria, greater than the cost of capital. However, if they are mutually exclusive, accepting one rejects all others, even if they're profitable. So if these were mutually exclusive projects, we're evaluating two machines that do the same job, we only need one. We pick the best one. So this we're a mutually exclusive situation. I would accept A because 13% is bigger than 12. Yeah, B would still be profitable, and its net present value would be positive too, but A is even better. So if it's mutually exclusive, you only pick the best one. Now I'm going to go to the sideboard over here, and eventually the camera's going to catch me. And I want to show one other thing that's important to you. And this, by the way, on page 492, figure 12.4, is a table, is a graph, very similar to what I'm going to draw here. Okay. So if you can't see this too clearly, you can still pick up on it in that chapter, even though we're not dealing with that chapter per se in the course. It's a very important table or graph. I have internal rates of return on the y-axis, 6%, 8, 10, 13, 14, whatever. Okay. On the x-axis, I have dollar amounts, how much each project costs. And I'm going to say that I've got 4 projects here. Project A, B, C, and D. And I've got their internal rates of return. Project A has a 13% rate of return, B is 10, C is 9, D is 6. I also know how much each one costs. Okay? Project A costs $1 million, B is $500,000, C is $1 million, D is $2 million. I'm going to graph this on a line, okay, on my graph here. Project A has a 13% rate of return, and it costs $1 million. So I'm going to start my line at 13%, and I'm going to draw the line to represent how much it costs, and it costs $1 million. So it's going to go from here to here. Okay, so that line is $1 million long. My next best project, I don't just in alphabetical order, I do it in terms of decreasing internal rates of return. My next best project is 10%, that's right here, and it's only going to cost $500,000, so my length of my line is only going to be $500,000 long. C is 9%, and it's another $1 million, so that gets me up to 2.5. And now we have the clunker, D, 6% rate of return. Here's 6%, and it costs $2 million. What this graph shows you is something very important. Note there's a horizontal line right through the middle of the graph, right here. And I've labeled that my weighted average cost of capital, right, at 8%. Anything above the line, internal rates of return greater than cost of capital, we accept. Anything below the line, we reject. But the neat thing that this also tells us, these are independent projects, and we have unlimited funds. We don't have a budget constraint. If I choose these 3 projects, and these line segments tell me how expensive they are, and I drop a line down to the x-axis at $2.5 million, it tells me what my capital budget is. Okay. Now, if I had a budget constraint, and I only have like $2 million, then I wouldn't be able to do C either. But here I've got unlimited sources of money. I like the federal government, right? So this graph will tell you what projects you're accepting, all by internal rate of return. If you're rejecting any projects, and also what your capital budget is. So it's a very interesting graph to understand. And the weighted average cost of capital line goes right here. I'm going to say one thing that you are not responsible for in this course, but if you eventually go into an MBA program, you need to know a little bit about. I'm going to do very little with this. This weighted average cost of capital line I drew as a straight line, right, horizontal line. It doesn't change. Well, sometimes your weighted average cost of capital can start going up. For example, if the bank will loan you $1 million at 6%, but if you want to borrow any more than that, they're going to up the interest rate, which would be kind of normal. That will raise your weighted average cost of capital. So you might have a situation where this line no longer becomes purely horizontal. It might do something like this. The bank loans you X amount of money, and then if it's going to lend you any more money, the weighted average cost of capital line goes up. Ruh-roh. Now it's above choice C, and we end up rejecting C. This is called, where the line breaks, a break point. Again, you're not going to have to deal with this in this course, but if you do go into an MBA program or in some of the follow-on finance programs, courses rather, you may see this term, may hear this term, a break point. All it means is the cost of capital went up because we were borrowing more and more money, or we had to switch to more common stock or something like that. So the line can actually break and go up. That can happen. Just wanted to make mention of that. Okay, so payback, which is simple, very easy to do. I think in my writings I said even your boss can understand it. Net present value, which gives you an answer in dollars and cents. And then internal rate of return, which gives you a similar decision of net present value, but it gives you the answer in terms of a percent or a rate of return. I think what I've written in the book also will help you go through these last two very important models. Okay? So as always, thank you for listening.